2, -1, e to the t. Alrighty.
Huzzah.
We did it. So occasionally these problems do take a little bit longer. Occasionally. Just because we do have all of the portions that we're going to look at and say, like, okay, we've got to focus on the null space solution, so now we need to get our eigenvalues and eigenvectors. Then we need to focus on the non-homogeneous portion, and with that, we used a particular method in order to find our coefficient methods, or sorry, coefficient matrices or vectors, and Zach, you want to give that one away? The name of the method is called?
Oh, this one?
Yeah.
I would have called this undetermined coefficients.
Yeah.
Or I actually learned from a professor here at my university, called it the method of inspired guessing. And that's what...
And it is, really. I mean, we're saying, well, I'm pretty sure the solution must have a portion in it which is the same as each of the portions of our non-homogeneous portion, I'm using that word too much, of our differential equation. So using the method of undetermined coefficients, or inspired guessing, we can say, alright, I'm pretty sure that this is going to involve each of the pieces which are in this separate vector, and now let's just say each of those portions is going to have its own constant vector, and then find out what those vectors would have to be in order to get that. There is also another, I suppose, another way that we could have said, like, you know, g of t in this particular case is the portions again were e to the, e to the negative 2t times a vector of 1, 0 plus a vector of 0, -2 multiplied by e to the t. So this would be the portion that goes into our differential equation, and we talked about earlier as, oh look, this is g. And we should be able to find, again, using undetermined coefficients, what each of those individual vector matrices needs to be. And then eventually we work it down and find it. Alrighty. So... have over here, is this all the same stuff? Looks like it. Okay. Sorry, just had, yeah, okay. Yeah, it's the same one. I was looking at 2 separate days of notes on my differential equations class, but I ended up, you know, half redoing a problem or something like that. Hey, Sensation, how's it going? Well, we spell it slightly differently. So it is not just homogeneous, unless that's what I did. always possible that I wrote it wrong somewhere, but yeah, there's an E. At least in American.
In American.
That's what we've taken to calling it over here. Since we moved. Alright, let's see. There is also... Let's see, do I want to do that? Yeah, let's go for it. So there is also another method that we can use for cleaning up our particular systems fairly nicely, which is that if we say we want to get the particular solution... Sorry, that was lowercase in the other one. No, it doesn't really matter, but still. One thing that we can do is say we've got a times our x particular vector plus our g vector like we had before. And what we can do is let x sub p be equal to t times some other vector y, where, have to define our terms, y is an unknown vector, which we can solve for. And t is an... I'm using the word appended, but I don't think that that's necessarily true. Concatenated?
I guess what are you trying to say? You have the where y is an unknown vector and t is multiplied.
So
I would just say multiplied.
Well, no, that is true, but what we're doing to get t, like to make t in the first place, is to take our eigenvectors.
You're slamming the vectors together. Yeah. You're combining your. Yeah, I mean, I guess you could say like glued. That'd be informal, but you could say appended or concatenated. I think all of those capture what you're doing. You're talking about how T is built.
Yeah.
Okay.
So in this particular case, right, T is just taking our two eigenvectors that we had, which were, let's see, we did, which way did we do it? It's down the bottom here. Oh, curses. I use the ones from the beginning. That's fun. No. I think maybe I didn't have... Yeah, that's probably okay. So what we can do is we can take our vectors that we had from the very beginning. So it was 2i, 1, and negative 2i, 1, and use those instead. This is actually more likely what's going to happen in the first place. If you're going to be doing this method, you're going to be plugging a bunch of this stuff into, you know, a matrix calculator. You're not going to sit there and do it by hand. I'm only doing it by hand because Mr. Pez here absolutely loves doing stuff by hand. So, gotta show how it works first. So instead of listing our eigenvectors as like two separate things, we're just going to bring them together, snap them together like magnets, and say, there's our T matrix. So 2i, negative 2i, 1, 1. Okay. So going back to the original statement here, where we're trying to figure out what x sub p our matrix is going to be, we're going to say, let this be t times y vector, and that's going to be prime. Is equal to a times the same plus g vector. All right. Zach, where can we go from here? Like, or just algebra-wise, like, what's available to us?
Okay, so you've got some t, right? It's t vector.
Yep.
All right. Okay. So, I mean, you could try multiplying stuff. Like t is a is an eigenvector matrix.
Mm-hmm.
That's what we're doing. Okay.
Yep.
So, I mean, one thing you could do is you could try to diagonalize things. Like, that might be a good idea. I'm thinking about, like, the reason to do that is, I mean, you're basically factoring the matrix into two messy but nicer, have nice property matrices, and one really nice property matrix, if that makes sense.
Yep. How do you diagonalize?
Well, I mean, I think it's useful to talk about what this is doing. The diagonalization. You've got your T matrix. Those are your eigenvectors.
Mm-hmm.
But you're going to turn A into a product of three things. You're going to take a matrix T, but you're going to have also the inverse of T, and you'll have your D in the middle, which is your diagonal matrix. In principle, what that's doing is what's called a change of basis. I don't know how far you want to go into that, but like you're doing some transformations that will basically get me the same matrix back. And this what, am I saying things you want to be going into, or
Yeah, sure.
to be quiet and all? I don't know if we want to go there, because we can.
The idea of like why this is at all important is at least nice to, even if we don't understand all of the little bits about it.
Right.
Like.
Right, and so I guess what I'm trying to say is, what I would suggest is multiplying by a T inverse, and I would recommend not have on the left, left multiplication. Yeah, that does matter, doesn't it? The reason for that, and just I'm being persnickety here, but the y here is a prime alone. I don't think we need to differentiate T.
Because?
T is, what is T? T is a constant matrix.
Yeah, exactly.
You're not going to want to do that.
Even if it's in complex space, we've already figured out, like, it doesn't really matter. And anybody who's overtaking Penn's class is going to know this. But right, anytime that you've got just constants, I is also a constant, so we're just going to be multiplying a constant matrix T by our function matrix Y. And so that's the one that's going to get derived. Alright, and how do you feel about associativity?
I feel great. I mean, associativity is a thing too. But that's matrices are associative, so we should be okay. And so the reason to do all this is you have T inverse AT, and then you have a T inverse G, which we'll handle in a minute. But that T inverse AT, that basically is diagonal now. The advantage is that is going to be a diagonal matrix, and the things along the diagonal are eigenvalues, which is really convenient because diagonals along the eigenvalues are about the best as it can get. Like, you got a diagonal matrix, and you try and solve this. That's at least reasonable, in some sense. Now, the reasons as to why that's diagonal, I mean, if we want to go into all that, I don't know. Like, that can take some doing. But suffice it to say, this will be a diagonal matrix.
Yeah. So, let's see. At the very least, we can do the example that is sitting before us. So if we end up doing the... Oh, come on. Determinant of t is going to be 2i plus 2i, so 4i. And t inverse is therefore going to be 1 over 4i multiplied by the matrix that is, what is it, negative along the main, and swap the off. Is that the cheating shortcut way?
I think that's right. You take negatives and then swap.
Yeah, oh no, it's swapping the main diagonal. Man.
Mm-hmm.
Alright. Oh well.
and that's negatives along the...
Yep.
The other.
Okay, so then with this, gonna get a 1/4 multiplied by, and if we divide by I, that's also the same as multiplying by negative I, or I to the third.
Mm-hmm.
So we're gonna get a negative I here and I here, and then we lose the i's on the right-hand column. Alright, so this is T inverse. So if we multiply T inverse by A, we get that 1/4 negative I to I2 with -1, -4, 1, -1, which is 1/4 times the matrix. So here we're going to get a plus I plus 2, and then we get a 4I minus 2. Lower is going to be a negative I plus 2 and negative 4I. Minus 2. And then T inverse AT is going to be 1/4 times all that stuff. Multiply by T again. Which is going to be equal to 1/4 times the quantity. Here we get 2I times I is going to be a -2. Okay, plus 4i. And then we get 4i minus 2 multiplied by our 1 at the bottom. No. Hang on. Did I mess it up?
Let's see. So you've got
No.
I plus 2, 4. Yeah, we should be all right on the first line.
Although I've got a problem here because now I've got a plus 4i.
Uh-huh. Well, yeah, so we could have messed up the inverse thing.
Quite possibly.
Let me think here. I forget it too, so don't feel bad. I've done so. If you can scroll over a little bit, I can try and find where the problem is. I just can't. The stroke color thing. Was in the way. So T is that. So then we're going to swap those and change the sign. That's great. T.
Oh. Yeah, the multiplying by negative I.
Yeah.
I didn't do that in... No. No, wait, I did. Right, because you multiply I by negative I, you get I to the 4th, so that's gone, so it's just 2's. Okay.
Yep. Yeah, you should be okay there. Yeah, okay. I'm going through and checking the math.
Yep.
Then you've got minus 2 plus 2. Oh. That would be... Okay, so look at the last line. The I plus 2, 4i minus 2 times 2i 1. That should be minus 2 like you have. And then 2 times... Wait. Right. That's fine. Yeah, no, that, and then the upper right entry should be 0. That should be fine. What you have. What you have, it looks good, actually.
Because it's right. Oh my. Yep. No, I'm good now.
And then you have the 4th. That's gonna be what does it. Because
Right,
you should get a minus 1 plus 2i.
I forgot what we were doing. I thought, oh no, we should end up with the identity matrix, but that's not what we're ending up with.
No, you're looking for diagonal entries.
Yeah.
The eigenvalues. That's right.
Okay.
I was like, no, it looks
Sorry
okay,
about that.
but no, you're fine.
Here we go.
Fine.
Right,
there's a lot going on. So
negative 2i times I is going to be 2. All right, then negative 2i times 2 is going to be a negative 4i. Then we get, again, 4i minus 2 at the bottom. Or from the bottom entry. Okay. Then down here, we're going to get same deal again. This is going to be negative I plus 2 times 2i. So we get a positive 2. And 2i times 2 is going to be a plus 4i. And then
just a moment. I'll be right back.
No problem. Minus 4i minus 2 times our 1. You get that. And then the last bottom row, last column, is going to be a negative I plus 2 times a negative 2i. So we end up with a negative 2i times I squared is going to be a negative 2. Okay, and negative 2i times 2 is going to be a negative 4i. And then we get a negative 4i minus 2 times 1. Alright, there we go. So now we get a 1/4 times the matrix. Here we have, at the top, 8i and a negative 4. So negative 4 plus 8i. Top right, we have 0. Bottom left, we have 0. And bottom right, we also have a negative 4 minus 8i in this case. Okay. So then, when we factor out a 4 from all of the stuff on the inside, this is going to be a 1/4 multiplied by our 4 from the inside, gets us a negative 1 plus 2i, 0, 0, negative 1 minus 2i. Alright, so at the very least we can verify in this particular case that this inverse t times a times t is going to get us a diagonalized matrix with with our eigenvalues along that diagonal. So we end up with here, this is going to be y prime like that. This is going to be 1
I'm back, by the way.
plus,
so just so you know.
Cool. 2i, 0, 0, 1 minus 2i. Thanks for the heads up. Times our y vector plus, and now we get again our generalized, in this case, t inverse times g. And this is one of the other things. We know what t inverse g is going to be now, because we have t inverse, it's a constant, and we have g from the very beginning. So that's going to allow us to clean up a few of these things. Everything's the same kind of math, just written differently? Yeah, pretty much. How you doing, Anders? Oh, nope, that's not Anders. That's Lizioma. I'm sorry. I forgot. You added characters at the beginning of your name. Alright, at this point, there's multiple ways to do this. In this particular case, we can break this down into two separate equations, which the first one is going to be y1 prime is equal to, and up here we get a constant 1 plus 2i times y1. It's going to be added to, and now we have to do the t inverse g, which I didn't do yet. That's fine. So we have t inverse here. So we get our 1/4, come on. Multiply by negative I, 2, I, 2, and then multiply by our g vector, which was, again, e to the negative 2t, and negative 2 e to the t. Okay, this is going to be 1/4 times the matrix. And this is now going to be negative I E negative 2t minus 4 e to the t. And second, I e to the negative 2t. And minus 4 e to the t. So now all of that can follow us back. Say we're going to get rid of our matrix portion and just create two separate equations. That one's going to be down here. That one's going to be up here but slightly straighter. And then we multiply both by 1/4.